G'day there. You're watching the Aussie BIM Guru, and today we've got an interesting topic on the channel, which is running sun hour analysis for Revit using Dynamo. It's actually a query that came up on the forums a long time ago, probably about a month or two ago now, and at the time the moderators on the forum recommended using VASA or voxel analysis, which in my opinion is a pretty wasteful approach. So I decided to show that it's completely possible to do this in Dynamo without resorting to complex methods such as that, but also that you don't technically need Grasshopper and Ladybug if you absolutely don't want to use it. Having said that, I'm a huge advocate for Ladybug tools, Grasshopper and Rhino 3D for analysis like this. Dynamo is simply not the right tool for this job in a lot of cases, especially if you have a complex context model. Having said that, this is totally viable when you're doing super simple and early design analysis, but for refined and accurate solar analysis, I would usually recommend resorting to things like weather files or EPW files, which Grasshopper and Ladybug work with really well, because it's accurate weather data and it doesn't have to come from inside the black box that is Revit. But this is a good workflow if you either can't access or use Grasshopper or Ladybug for various reasons. Maybe you're just not very familiar with Rhino or don't really feel like learning it, or you prefer to use Dynamo. But I highly endorse learning both approaches. In my opinion, Ladybug and Grasshopper is industry standard for sun hour analysis. Anyway, today we're going to be looking at firstly how you can process basic testing surfaces in Revit using Dynamo, using what we call their ISO curves and using some mathematics and functions to figure out how we can place a relatively even grid across a test surface. From there, we're going to use some interesting techniques in order to get sun directions at particular times of day across a time range. So very similar to the process we would do in Grasshopper and Ladybug typically. I'm really just recreating that process. We are going to use the sun direction in Revit. I'm not completely trusting of this data. I don't know if Autodesk keeps it up to date. Typically we use weather files that come from airports at very specific places in the world for proper solar analysis. So just be aware that sometimes the sun direction in Revit may not be the best reference. From there, we're going to actually run a Raybounce test. So we're going to run a sun hour analysis in a similar way to how you would do it in Grasshopper using MeshRay. And from there, we're finally going to return these results to Revit visually using a little 4-point adaptive component panel. So a fun little workflow. It's going to be quite complex, but we're using Revit 2022 and Dynamo for Revit today. We're using a tiny bit of Python, so if you're using 2023 and beyond, some of the Python I use might not work exactly as it does here, so just be aware of that. In this case, I was using Crumple originally. You don't actually need Crumple, so a bit of a correction there. It is assumed there will be some knowledge you have already of just the basics of Revit family management and model creation. You have a fairly fundamental basic understanding of Dynamo and hopefully code blocks, because we're going to use a lot of code blocks today. As well as that, we will use a little bit of Python and Revit API to get the sun directions, which is really what unlocks this whole workflow in the first place. So hopefully you have a little bit of understanding of that. But without further ado, as always, if I'm talking too fast, feel free to change the playback speed, but otherwise, let's dive in. So this is effectively the goal of our study. In this case, I'm just working with a fairly simple model, and we're testing this particular building mass to see the sun intensity across the course of a day that it's exposed to. We can see that some areas are more exposed than others, and we're using, in this case, a color gradient to represent this. We can see here this is based on the value of a custom parameter I've set up called sun hours, and I'm using an adaptive component. So we're going to use Dynamo to measure the results at these areas and then place an adaptive component and set its sun hour value to the maximum number of hours received at that point. In this case, we're using, I believe, filters to achieve this. So we can see there are various filtering criteria here occurring in order from top to bottom. So the first result is 7, after that 6 plus, 5 plus, 4 plus, etc. to represent the number of hours at each point. And as you expect, you'll get less sun hours received at areas around corners. For example, here we only get an hour and a quarter. In this area we receive 4, and in other areas we receive less depending on the area that we're measuring at. So you can see right behind there, obviously you almost get no sun. You really just get the smallest amount, I believe, either right at the end of the day or during midday. As well as this, the project at the moment is currently just facing true north, but we will add a method to compensate for this in the workflow as well. For now, I'll just keep it true north, so it's really easy to test and visualize what's going on in the project itself. So I'm just going to jump straight into Dynamo, and we're going to begin working with this script. Now I am going to use just a little bit of pre-written Python that is just a lot easier to start with as is. You can always download my sample file and isolate this if you're trying to build along with me, but effectively this is what we're going to use to actually get the sun direction in Revit. I might just quickly go back a step and just talk about the fact that getting the sun direction in Revit is really easy for a single time of day, but to do it for a range of time, it's a little bit more difficult. So currently this view is set to a still 11:17 a.m. sun setting, and we can actually access this sun setting using the Revit API and also get its properties such as its facing direction, the altitude, azimuth, etc. But we can only do it for this particular sun setting. So we're going to end up actually iterating across and changing the sun setting in the background from another view and asking it at each point, what is your vector? So that's pretty much the trick to making this work in Revit without needing a weather file with vector data. So in this case, we're going to be using the sun and shadow settings. In this case, we'll get that as a class or an object. And this will allow us to ask for a lot of information about it. We'll do a little bit of transformation, but it's all going to be done in this Python script that we'll probably just look at once we get to it and just explain what each line of the script is doing, because there's a much broader script here to cover, not counting that itself. So what I'm going to begin doing is basically scripting a method to take a face and subdivide it into workable subfaces like this. Effectively, this is a sampling technique pretty commonly used in any sort of study like this. So I'm just going to begin with a select face node, and then we're just going to go straight to Dynamo. So I'm going to select, in this case, this face, and then we should be able to see the preview for that in Dynamo. So that is effectively our test surface facing this way. So we'll keep that in the background so we can sort of see what's happening as we work with this particular object. So what we need to do now is break this thing down. So I'm just going to move this over here. We need to break this thing down into divided pieces. So how do we know how many pieces we want to divide this into? Well, we could use a package called Lunchbox. I'm actually just going to skip using Lunchbox because it is difficult to get that package these days, and I'm going to build it myself. So in this case, I'm going to use the get isoline method, which will effectively get a parameter-based curve on the surface. So even if our parameter has a trimmed surface, it's going to get the untrimmed ISO line. So what we can do now is just get, so you can see at the moment we're providing an ISO direction of 0, and currently this is giving us the vertical ISO line of our surface. But I can, in this case, feed in both 0 and 1 as a list and set this to longest lacing, and we should now get both the horizontal and vertical ISO line. I can use these to determine the size of my surface, so I know roughly what I need to divide this into. So in this case, I'm going to be using a function. We don't use these often, but sometimes if I'm doing something twice, I prefer to turn it into a function in a code block instead. So what I might do is just build it once and then maybe turn it into a function afterwards. So I'm going to take, in this case, just one of my ISO lines. I'll just say P1 is equal to curve input 0. So we're just going to take our first ISO line, which should in this case be that vertical line there. So to this, I'm going to begin by getting its length. So I'm going to go curve dot length, and I'm just going to, in this case, take the curve's length. And I'm then, in this case, also going to take, in this case, the increment. So in this case, I'm probably going to have a spacing that I'm targeting, so I need another input. So I'm going to say increment is going to be equal to spacing. So I might just say, in this case, the increment is the length on S for spacing. And if I need to do a colon here, and I can now add another input. So let's say this is our target grid spacing, maybe 2.5 meters, 2,500 in millimeters. And at this point, I know I've currently got both curves coming through, I believe. So I really just want one in this case. So what I actually need to do is do P1 here. So I now know, with rounding applied, how many divisions we would require to achieve that spacing. But in this case, I want to round this up because we're not going to go larger than the maximum spacing. So in this case, I'm going to say spacing is actually going to end up being, I'm going to say math.ceiling of the length, sorry, the increment. So we can see now this is forced to become 5. And I might actually just call this CEI for ceiling. It's easier to remember. And now I can say, in this case, well, the spacing is going to be the inverse of that. So I now know, in this case, that's gonna, sorry, not spacing, one on, I think I've tripped myself up here. I'm sort of following a recipe I used before. So I might leave out the spacing for now. It's probably easier. I think that's gonna be the parameter that we divide these objects by. So I might just leave this for a second. I might explain this later. Return to this. But what we're going to do now with our ceiling is we can now divide our total length by the ceiling to know the width of each panel that we're going to require. So I can now say in this case the ceiling is equal to the length, the new ceiling, spacing. I'm just going to do SPC1, SPC2. So we now know that we need to have 2400 wide panels in order to achieve this. So we can see it's almost 2500, but because it's our max spacing, obviously it's going to be lower or equal to at best. From this, we can now create a sequence. And in this case, we actually want to create a sequence of UV parameters to place these points across that curve at, because we effectively want to create a grid of UV points in both directions as close as possible to that. Now we've effectively got our parameter, or our spacing parameter here, which is 0.2, because we have 5 panels across a domain of 0 to 1 of the curve. So we're going to use this in order to create a domain which will let us place points at the center of each panel. So if you can imagine, currently we're going to have points in a sequence that start at the beginning of the curve and end at the end of the curve minus 1 point of domain. So it'll go from 0.2 to 0.8. We actually want to move these by half of a spacing in the domain, which we have here in spacing 1, so 0.2. So we actually want to move these 0.1 to forward in sequence, so that we're between each point of the domains of the panels. It'll make a lot more sense once you can see this visually represented, so I'll just sort of work my way through this step. But we're going to create a sequence, and I'm going to say the sequence is equal to half of the spacing in the domain aspect. And I'm going to go to 1 minus the spacing on 2, and in this case I'm going to have a ceiling, so that the required number of panels in the domain. Now I think in this case I have to say spacing 1, because I've called this spacing 1. But we can see now we have 0.1, 0.3, 0.5, 0.7, and 0.9. So if I make this say 1500, we can see whilst we're going to have awkward numbers, we're still going to be in the middle of each point along that domain. So for now I'll just say 2500 again. So now that I have this sequence, effectively I can just return these values. So I'm going to switch over to a function at this point. So to change this to a functional notation, I'm going to have to disconnect my inputs. So I'm going to get some errors for now. But I'm going to write def, and I'm going to call this get parameters. I'm going to provide 2 inputs, which I'm going to call CRV or curve, and S for spacing. I then go to my new line, and I use this curly brace to imply I'm beginning a statement for a function. And I'm also going to need to return some things at the end of the function. So I'm going to return, in this case, a list, which will contain both the sequence, so SEQ, which I'm calling this, and I also want to return how many objects we ended up needing. In this case, I might actually, I'll see. This will be like the cell size, if that makes sense. We're probably actually going to return the incremental spacing. And I'm also going to need to just go to a new line and put a semicolon here. And this creates a function that I can now call on from other code blocks. It's not a technique I use often on the channel, but I thought it was a good one to revisit. So that part of the script is pretty complicated, right? There's going to be a few things that probably take a little while to understand exactly what I'm doing there. I'll just get rid of that for now. But now that I have this function, if I send any curve into this function, I should now get both a sequence or an incremental spacing for a panel on that ISO curve. So what I'm going to do is create another code block, and I'm just going to use this function on both the first and the second curve. So I'll say P1 or part 1 or parameter 1, and I'm going to use get parameters for curve 0 with spacing S. So it's going to ask me, of course, for 2 things here. What is curve and what is spacing? Curve is my list, spacing is S, is 2500. And I should now, in this case, interesting, I'm not getting anything. That should be returning something. Sequence should definitely be returning something. Bear with me. Curve 0, S. Interesting. So I might have to, I need to put curve in here instead of P1 now. There we go. So we can see now the function is able to actually work on this object. We've returned both the domain and we've also returned the spacing or the size of this particular panel. And I believe 4.8 doesn't seem correct. So I'm just going to double check. I might actually want to be returning the increment, I believe. No, I want to be returning the spacing. Spacing 2, I think, is actually what I want there. I basically want the size of my tile in millimeters. There we go, 2400 is what I want. So now I should have what I need to effectively generate these panels at particular points along the surface. Now I'm going to do that for both ISO curves. So P1 and P2, curve 1. And then I'm also going to just isolate the parameters by calling out the indices. So now I'll break out the sequences into objects, and I also want to get the cell size for later. So that effectively will be my cell size in both directions. Sorry, 0 and 1. So I might just add some comments here. In this case, this will be my parameters, and then the other one will be my tile size. So now I can evaluate my surface in both directions by using cross products of evaluation at parameter. So I'll show you what I mean by that. So I'm going to use a point at parameter node, and this is where it's all going to sort of start making a little bit more sense. I'm going to get my surface, and in this case, I'm going to call both the U and the V domain, and I'm going to apply these as a cross product. And we can see what this has done is it's created my set of center points in both directions, and it's run across this row by row. So we now have our testing grid upon the untrimmed representation of our surface. I'm going to want to flatten this because I don't really need those points in a regular order anymore. And I'm also going to want to get the normal at those parameters as well, because maybe sometimes my surface might be curved and it may need to assess a normal based on that as well. So I'm going to ask for the normal direction at those parameters on a cross product basis as well, and also flatten that particular input. So it's a fairly complex part. Now it gets a little bit easier now because really we're just dealing with test points. We've got an issue here in that we have some points that aren't actually in our test surface that we don't want. So I'm going to use the does intersect check because these objects should be within the surface if they intersect. So I'm going to say do these points intersect this surface on a longest lacing basis, and we should see which points do and don't intersect with the surface, which we can then apply via a filter by Boolean mask to just get the points that do actually sit on that surface. And likewise, we can also take the normals in the same aspect. So now that we have the points, I might just do a code block so we can see what made it through. So we can probably just actually say X. So we can see here, this has effectively excluded the points that don't sit upon the surface. So what I can now do with these points is actually create rectangles to represent these as tiles. So before I do this, I'm actually going to want to push these points away from the surface so that when I test them for a ray, the ray isn't going to intersect the surface itself that these came from in the first place. So I'm going to use a geometry translate node to push these away from the surface with a direction and a distance. That's why we've got these normals at parameters. So I can now take these points in these directions by a given number. So let's say we want to move these maybe half a meter away. Well, we can now see that our test points have been pushed off the surface by that distance. So now they won't be clashing with the surface if we run a ray test on them. So in this case, I might just set this as an input and say this is distance from surface. And I might also just go back and say this is target sample spacing. And this is just going to be select face. So now that we have these points, we're now going to want to turn them into a testing grid, a visual testing grid, but also one we can use to place adaptive components later on. So in this case, we're targeting a rectangle by width and length, which also requires a placement plane, which will both orient and position the center of that rectangle. So I'm going to create a plane by origin normal. And in this case, as you can guess, the origin is the center point and the normal is going to be the normal at parameter. From this, I can take this placement plane and get both the width and the length, and voila, we now have our testing or tile grid. Now, if you want, you can actually technically put these back at the surface, so we don't technically need these to be offset. So I can always take the original location point and push them back. But what I like to do at this point typically is just isolate what I really want to see. So I'm going to turn off these preview points, and I'm also just going to, in this case, turn off my test points, but understanding that they are going to be used later on in the workflow. So I might just make a code block for now, so we can see them, and just call that test points. So at this point, really, we have the first part of our script covered. So I'm just going to create a group and say generate test grid. So a fairly complex workflow up until that point. The bad news is it's going to get a little bit more complicated. But what we're doing now really is trying to create some temporary solar settings to check the direction of the sun in Revit. So I'm going to begin just by creating some inputs which will suit a solar analysis. So I'm going to make an integer slider between 1 and 12, which of course will be month. I'll probably just make a number for the year and just say 2022. Now I might actually do an integer slider, so I will actually do another one, and I'll make this one between 2022 and maybe 2030 for now with a step of 1. I'll call that year. We're just going to do a single day but a time range, so I'm going to say day. In this case, I'll make this between 1 and 31 and set it to 21. And I'll set the month to June, the winter solstice, when the sun is lowest for now. And then we need to create a time range. So in this case, I'm going to create a few inputs. I'm going to use probably 2 sliders for the start and end time in hour. So in this case, I'm going to go between 0 and 23 with a step of 1. I'm going to start at 9 AM. And I'm going to currently finish at 15 AM. So I'm using 24-hour time, which is quite important as well. And from this, I'm going to create a range. I'm going to go from start to end with a step of 1. And I'm also just going to check what my end minus my start is. So what is my duration of study? So start, end, and I should have now 1 hour represented in each. And I also know that I'm dealing with a 6-hour span. In this case, well, 9, 10, 11, 12. It's technically a 7-hour span if you think about it. So we could always manipulate that later in the script, I think. So I have my hours, and I'm also going to work with a time step. So in this case, this is how many minutes we're dividing, or how many steps we're dividing our hour into. So I'm just going to make this an input and call it time step. So for now, let's work with a quarterly hour interval. So now we need to actually create our date times. So I'm going to create a code block. And first of all, we actually need to create our sequence of minutes. So I'm going to say seq is a sequence from 0 to 60. And the number of divisions we use is going to be, in this case, 60. And we're going to divide this by the division plus 1. So if I provide my division, we can see now we have 0, 15, 30, 45, and 60. Now in this case, we don't actually really want that last increment, but we'll keep it for now. So what I'm going to do is say that we need to know how many things are in our sequence. List count sequence, so we know how many steps we ended up using in order to divide by that interval. And I'm just going to now also, for later on we're going to need this, I'm just going to say count -2, and we're going to use that later for a temporary purpose. But we also want to say that we want to remove item at index, and we're going to take our sequence, and we're going to minus the count -1 is the index we want to remove. And that should now leave us with 0, 15, 30, 45. So if I do 10-minute intervals, we can see now we get 0, 10, 20, 30, 40, 50. So it's pretty useful if we want to create minute intervals that we test at as well. So let's stick with 15-minute intervals for now. So from this, I'm just going to line these all up, and we're going to use these all to create some date times. So I'm going to just do the date time by date and time. So we can plug in our year, month, day, and we're going to use our range for our hour, and we're also going to use our minute range. In this case, we're going to be using this sequence, and second will remain the same. At the moment, this doesn't really give us a desirable outcome. We need to work with a cross product, which will now give us all the times per hour broken into sublists by hour. So we don't want to test beyond the last hour, we just want to test at the last hour. So in this case, we're going to try and just target keeping 3 o'clock. So from this, we're going to need another code block. And in this one, we're going to say, first of all, times is going to be flattened. So we're going to make times as a list, and we're going to use the list flatten. And we're just going to apply this to an object we're calling date times. And now we should have just all the times in a big list. We can now say, in this case, we want to find out how many times we need to take off the end. So I'm just going to say indice or ind is equal to list count. And we want to know in this case how many date times we have. So we're going to count the number of objects in times. And we're going to create another variable called excess. So excess in this case is going to be the count minus 2. So we know this is how many objects we want to remove. So we know we want to keep 25, in this case 25 objects from our list. What we're going to do now is just take all the items before that index. So I'm going to say lists.takeItems, and I'm going to take my times list, and I'm going to just take until we get to the indice that we just generated. And we can see now that we end up with the last interval being 3 o'clock. If I change this to maybe 10, we can see those counts still get us to 3 o'clock. So we've now successfully developed a way to generate a time range. So what I might do now is just block these off, because these basically generate my date time. And then this section actually generates my desired datetime objects. So now that we have these, we're going to want to actually generate some temporary date times. So what I'm going to do for now is probably just create a new 3D view at just a origin point. So I'm just going to make an axonometric view. And this is really just a temporary view. We only need it when we run the script. So the I point in this case, I'm just going to use just a point that's not at the origin. So I'm just going to say point by coordinates, and I'll just say 1, 1, 1. And then that can be the I point, and then the target is just going to stare for now at the origin. But we're going to be manipulating the sun settings in this view anyway, so it doesn't really matter where this view looks. It just needs to be a valid view. For now, the name, we'll just call it temporary or temp. And we're going to be generating an axonometric view on that basis. So I'll just call this dummy view. Now you could always use Python to generate this view as well. It's totally up to you how you want that step of the process to work. But for now, I'm just going to work with that. So this will generate me an axonometric view called temporary. I'm going to be using this block of Python now. So this part's a little bit tricky. I'm going to try and explain it just by going line by line through the Python. But feel free to copy this node from my sample workflow if you're trying to follow. So in this case, I'm taking 2 inputs. The first one is my view, and the second one is all my date times that I want to find the direction of the sun in Revit for. So inside this piece of Python, I'm just going to edit this node, and let's see what we're doing. So we have a whole bunch of imports to set up all the things this script needs. Probably a few of them probably aren't necessary, but we are, in this case, basically dealing with what's called a function in Python, which will try to change the date time and then ask that date time, what is your direction? So we can see here that we use a function which takes the view and a date time. So we're going to use this function for each date time for that view. And first of all, it just says get the sun settings of that view as an object. We then begin a transaction because we're going to change the time of the sun and shadow settings in that view. We're checking here just to make sure that the datetime object we have is going to be working in a local datetime system. If not, we just convert it into a local datetime kind. Not a super important step, but one to do anyway. And then after this setting the start date and time setting or property of the sun settings to the date time we're focusing on. From here, we're just saying that it's a still image because it requires that setting to be, in order to be oriented to a particular time. And at that point, our transaction is done. At this point, we're trying to find out what is the direction of the sun at the moment in that view. So we refresh the active view using UI doc, and then we regenerate the document to make sure that we're looking at the latest representation of that view in the model. From here, we're just asking for some properties. We're creating a basis Y. I believe this is for just a starting direction to figure out the difference between this and the sun direction. So we're asking the sun settings for the current altitude. There's a frame altitude as well that's coming from this, so we're finding out the altitude at that point in time. We're creating a rotation. This part is interesting. So I believe that we're probably compensating here for a property, I believe. It's a little bit complicated, this step. I have got this part off the forums. But I believe we're really just trying to get the actual true azimuth and altitude at this point. Where in this case, it looks like we're using some compensation to maybe turn some degrees. I'm not quite sure what that step does. But in this case, we're really ultimately trying to rotate this to find the direction of the sun. Interesting. So we're taking a basic Y vector, and it looks like we're just taking this through a set of transforms to get it to point towards the direction of the altitude and the azimuth, telling that vector to move by. So we're using those angles in order to move a basic vector in the Y direction. But what we get returned after running this once is the direction of the sun at that point in time. We've also got a function to unwrap all the objects in that list, and then we're using that across, in this case, I believe, our views. In this case, we only have one view, but we have multiple date times, so that function is not really necessary. We are unwrapping our datetime object. I'm not sure if you have to. I think you may potentially have to unwrap it. It's coming from Python, so I'm not sure if it's a necessary thing. I think because it's a Dynamo-based datetime, you probably do. But effectively, we create an empty list of vectors, and then for each time in datetimes, we run the getSunDirection function, which does all those things we just ran through. We then ask the sun direction from the current view, and we turn that to a vector and reverse it to point in the direction of the sun versus away. From there, we just append this vector. So if I run the script at this point, we should hopefully get one vector per datetime, and there we go. We can see that we're getting that result. Now, we can always test this. There's probably a pretty good way to test this. So I'll use an integer slider, and I'll work between 0 and 24 with a step of 1. And I believe in this case, it should be okay if I go to automatic mode. I think this shouldn't crash anything out. Spoke too soon. Good old Dynamo. Does not like doing automatic mode sometimes. That was a fatal mistake. Let's crash and come back. I'm not quite sure why automatic mode crashed that particular script. I'm not sure if it's trying to create that view over and over again, maybe. We'll just have to run this one step at a time. Fun. Another good reason why I just prefer using Grasshopper over Dynamo for this workflow. You don't crash very often. So we'll go back, and we just want to try and visualize each vector to make sure that we look like we're getting a pretty rational sun path. But we'll just wait and see what we get. I could probably actually take one test point and then visualize each vector from that point instead, just to show a sun path related to that point. So I'll just have to make sure I open up a backup of my script in this case to get the latest before I connected that automatic step. So solar project study, and we'll go back to Dynamo. And we'll try to visualize that sun path. Okay, so from my backup location, demo script, there we go, great. So that should hopefully take us back to where we just were. A little trick if you haven't done that before. Okay. Okay, so I think I won't go to automatic mode, I guess. What I will do is take those vectors. Great. And I'm also taking these points. I'm just going to take the first point. Doesn't really matter which one, but what I want to do is do start, direction, length. I want to do a line by start point, direction, and length. So in this case, from this point in the directions of the sun, and I might potentially want to reverse this. I'm just going to make this pretty long, like 50 meters. So So we'll get my geometry warning. Which input's not correct? Oh, rectangle, of course. I actually want to take the point, not the rectangle. And we should have, in this case, our sun points. They currently need to be reversed. So we're going to reverse those vectors as well. And we should hopefully be able to see our sun path at that time of year. And let's do a test. Let's change the time of year to when the sun should be higher. In this case, in December. And just make sure that that works. And there we go. We can see that makes a lot more sense. So I'm pretty confident this seems to be working and generating a sun path that is definitely coming from Revit. So I'm just going to go back to June and keep those angles for now. So I'm pretty happy with this. So now that we have our sun vectors, we can run a Raybounce. Now we could also compensate for project north rotation if we wanted to as well. So what I can do in this case is reverse those vectors like we just did. And I'm going to take a Z axis to rotate them around, and I'm going to use the vector rotate node. And I'm going to use an axis and degrees. So I'm going to rotate these vectors around the Z axis. And the degrees number we're going to use here is going to be the project rotation. Coordinates.project rotation. I'm going to do this on a longest basis, so each one will be rotated. And these should now be also taking into account if you have a true north rotation to make sure the sun is pointing to true north. So I'm just going to take these nodes and I'm just going to turn this section of my script into get sun direction vectors. So now that we have the direction of the sun and we have our test points, we can now actually ask each of these points to run a Raybounce against some objects in the model. So at the moment, my context and elements are all modeled as generic models. So I'm going to run, in this case, a filtered Raybounce. Actually, I'll just run a standard Raybounce, but just be aware if there are other things in your model that could block the sun, for example, these panels, which I'll get rid of, then you may want to potentially not have them visible in the view, because that will mean that they actually get in the way of the Raybounce. There are some custom packages like Bimorph and Data Shapes, which actually have Raybounces with the option to filter by category or include linked elements as well. But for now, I'm just going to do a complete Raybounce with all objects available to be hit. So I'm going to want to use Raybounce by origin direction in this case. So as you can guess, my origins should be my test points. My directions in this case should be the sun directions. Now, in this case, I'm going to want to work at each point on, in this case, all directions per point. So in this case, I'm going to say direction is going to be working at level 2. So I'm going to be working across all vectors for each point. And then I'm going to say I want to work on a longest lacing basis. So each point will work across each vector. In this case, the max number of bounces I'm going to say is 1. The current view will be the view that we're targeting, but I could also just take maybe even like the temporary view that we've created if I want to. But you could also take the current or active view in your model as well. So from this, we're going to get effectively a list of elements and points. So we can see if we look in our model, we've roughly got the abstraction from those test points where elements are actually going to be blocking our design from the sun. And they look pretty logical to me. We can see some points being blocked here, some points being blocked there. Now, the easiest way I found to process this outcome is to work with the elements, because we're only ever going to see the first element that we hit, if any. So we can actually count how many successful vectors are at each test point to find out how many results we get per point and divide that by our time step to know how many hours we actually receive at each point. So I'm going to do a list flatten. And in this case, I'm going to be flattening at level 3, I believe. I'll just check. Yes, so we want to basically get a list of elements per point, and that's going to be working at level 3. So I'm going to flatten at level 3. And now for each point, we should have a list of all the elements, if any, each of those test vectors have hit as array. So we can use this so we can count the number of results that have intersected. So we'll work, in this case, at level 2. And again, we'll probably do, I think auto is fine here. But we can see now we know how many things have abstracted each test point. So we have 112 test points and 112 results. So from this, we just now need to do a little bit of maths in this case. I believe we just need to say that in this case, we're going to be working with a few variables. So we need to know the maximum number of hours. And remember, we wanted to add +1 to this because it wasn't considering the last hour. So I'm going to say the maximum number of hours +1. And I'm in this case going to be subtracting from this the number of hours that have been abstracted. So we can pretty simply calculate this with just 2 variables. First of all, the count of the objects, and then the time step we're working with. So the formula for this is going to be, in this case, how many things got hit divided by 60 on the time step. So that we basically put everything into time steps in order to determine this on a minute by minute or a minute basis of how much time we've lost, sorry, hourly basis. So we're going to take the counts as C. The maximum in this case is going to be back here. And this is where we ended up with the E take S or the N take start. And then we're also dealing with D, I believe in this case. And D should be our time step. And this should now put us into hours regardless of our time step. So I can start to see some points are getting full sun, which as we would expect should be 7. Some are getting less, some are getting very little sun. So effectively we now have the ability to report at each point how much sun is being received. So we've effectively solved solar hour analysis on this basis. So what I'm going to do is just name this part of the script as well and say measure sun hours at point. So how do we actually visualize this in Revit? Well, there's a few ways we could do it. There are analysis grids or analysis surfaces. I really don't like using them. I find them quite complicated to work with and they don't always seem to work. So what we can do instead is place an adaptive 4-point panel to represent the polygon or the cell of the test grid, and then we can write the value to those objects, and then we can filter them using our view filters that we looked at earlier. So I've already got a panel that I've built earlier, but I'll show you how it works. So we have a sun hour panel family. This is a 4-point adaptive component. So I've created 4 points, created the reference line from 1 to 4 and a reference line from 2 to 3 and lofted between them. I've also added a parameter, in this case a shared parameter, so I can use it in filters in the model called sun hours. So this is a shared parameter. I'm then going to write the value to this, and then in this case all I have to do after that is just use view filters to override these objects based on their sun hour property. So what I'm going to do is go back into my model, and I'm going to firstly get the corners of the rectangles, which in this case I can do as polygons. So I can use the dot corners, and I can get the corners of the rectangle, and these are my 4 placement points for my cells. So I can probably just turn off some of the previews now. So I know at this point I'm really just dealing with the 4 corners. I'm just going to go and turn off a majority of my geometry in here as well, just because it is quite heavy now. I think that should be okay, and maybe we'll just leave the rectangles on as well. But we should be placing 1 adaptive component per point, and then we can set the value afterwards as well. So I'm going to use a family types node, and I'll just make this an input and say test panel family. And I'm just going to be looking for my sun hour family. And I'm just going to be placing a adaptive component by points. So in this case, the points should come in the form of sublists. So ideally you have a list of points. And then we have our family type. I'm just going to leave that on an auto basis. Before I go and create these, I'm just going to go and set their parameter by name. So to these adaptive components, I'm going to be writing to a parameter called sun hours, which I've added to the family and also to my filters. And finally, we're going to be writing this value to those panels. So I'm just going to make this a section of my script and just call this make panels and set values. So a pretty big script, fairly complex, quite a lot of stuff going on. But at this point, if I run my script, we should hopefully get a sun hour representation on this surface. And there we go. So if I hide, I probably need to hide a few things because at the moment there's a few things in the way. But if I isolate, maybe isolate these elements, it might be easier to see what's going on. There we go. I can probably also turn off the preview, and there we go. It's much easier to see. And there we go. We can see we're effectively getting a filter, applying a cascading set of colors to represent the sun hour result received at that panel. Now, because this is a full scripted workflow, I can go back and rerun this with various properties. For example, maybe I want to make a smaller sample spacing, maybe 1500 instead. Maybe I want to deal with I'll keep a time step of 15, but maybe I want to run a test in December when the sun is very high. I'll run it again. It's going to be a smaller increment, but effectively you'll see that we can very quickly change the criteria of this study. And there we go. We've now got a set of points. I can always just hide. And there we go. We can see obviously we're going to receive a lot of sun generally because the sun is very high. Of course, we can always also just undo and run this study back in the same month but with a finer resolution to get a better idea of exactly where sun hours are being received and where they're not being received. So I think in this case I might potentially need to run this through Dynamo Player. I've undone the creation of an object that's probably going to get removed because of element bindings. Are a really frustrating feature in Dynamo that to me is more of a bug. Sorry devs, that's my opinion. So I'll add, in this case, that, and what I'm going to start doing is running this through Dynamo Player instead. So I'm going to close this script, open Dynamo Player, and this way when I rerun the script, the adaptive components node isn't going to get stuck on element bindings and look for those same adaptive components that have just been removed. So demo script, select face, target spacing, I'll just say 2 meters. Distance from surface, let's say maybe 100 millimeters, we'll put it quite close. And time step 15, we've got our panel, run. And it should hopefully work in Dynamo Player. Here we go, here's our panels, and there's our values, excellent. And I might just for now, just really crank up the surface transparency here to 95%. We can also pick other faces, some don't have to be that regular. Remember, it's going to use the ISO curves of the face and then run an intersection. So we can see here we've got slightly different results here, but they do make sense from a color grading perspective that we can only typically get one aspect of the morning or afternoon sun. But you can very quickly just run this around your design and quickly set up a sun hour analysis. So you can see that I'm able to run these quite quickly on a form. Now you could try to build the script to do multiple faces at once. That's perfectly up to you. I don't recommend that because it would make the list management a lot more complicated. I'm not going to adjust the script to do that. But if you do use Grasshopper and Rhino, it's not too hard to set up a script to work that way. In Dynamo, because the sun hour analysis has to be written completely from scratch almost, it's a little bit different. But we can see we're almost done. We've pretty much done the whole building for this time of year. I just realized I didn't make the time inputs in Dynamo Player either. So that is one thing that's missing. But for this particular time of the year, we can see we've very quickly created a sun study. Now I believe because I've worked with ISO curves, we should be able to work with surfaces that aren't necessarily vertical. So I can probably also pick surfaces in the other direction as well. It's interesting, I can't, there we go. I'll just have to isolate this element so I can select the face more easily, but I should be able to pick flat surfaces too. So if you're doing like a public domain or a plaza, I believe this method should also be relevant to that scenario as well. And there we go, we can see we're also able to do these surfaces too. So it's a very flexible script. There are some limitations to how well it works. It really comes down to how good your base geometry is and how clean it is. Usually for solar analysis, I usually recommend keeping a pretty basic version of your building form. I wouldn't typically recommend usually trying to use detailed walls and objects that are highly detailed. It's better to do a test surface. Now this one seems to have had a problem. I think the face here believes that it belongs to this coplanar. It thinks it's coplanar, that's why. So that's a bit of a bug. So I think that comes down to the way that this is modeled, yes. So in this case, the way that I've modeled this means it's end up with a bit of an awkward outcome. I'd probably need to break this piece into a separate piece and then join it. Otherwise it tries to deal with that as one surface, which is obviously a bit silly. But Regardless anyway, we can see we've just undertaken a very quick and effective and logical solar analysis using Dynamo. A fairly complex workflow, lots of things that probably will need to be looked at in more depth for you to fully understand them. But I hope this is a useful technique if you're not able to access Grasshopper and Rhino for solar analysis studies like this. So there we have it, sun hour analysis in Dynamo and Revit. Technically possible and technically no Ladybug required as well, which was actually a reason why a lot of people couldn't do this in Dynamo eventually, because we lost access to the package once it was no longer supported. So you can actually find all the files today over on my GitHub. I know it was a really big script and I used a sample file, so you're more than welcome to download those files and try them instead. I'm probably not going to refine this any further, even though I know lots of people really want this workflow. I'm much more of an advocate for Grasshopper and Ladybug tools for this workflow, so if anyone else wants to take it further, feel free to, but hopefully it's a useful example of how you could refine this workflow in Dynamo and Revit. Anyway, if you're not already following and subscribing, feel free to do so. I make videos every week across various platforms, and we'll probably also cover some more Ladybug and Grasshopper tools videos in future as well that go well beyond what we've done here today. You can contact me at the email here, or you can also leave a comment if you have any video requests or queries, and I look forward to seeing you all in future similar videos. Thanks. Take care.